Across the vast plains and valleys of our planet, nature unleashes a spectacle of awe-inspiring power, the tornado. These whirling vortices of wind, often born from the fury of thunderstorms, leave a trail of destruction in their wake. While most tornadoes are fleeting, some monstrous storms defy the odds, carving paths of devastation for hundreds of miles. These are the long-track tornadoes, the true titans of their kind. Join us as we delve into the science behind these meteorological marvels, exploring the conditions that allow them to grow to such extraordinary lengths, and the indelible mark they leave on the landscape. From the infamous tri-state tornado that ravaged the American Midwest in 1925 to the behemoth that tore through Oklahoma in 2013, we'll journey into the heart of these epic storms and uncover the stories of survival and resilience that emerged from the ruins. In the realm of severe weather, a long-track tornado stands as a testament to nature's unyielding force. But what exactly distinguishes these meteorological titans from their less enduring counterparts? A long-track tornado is defined by its remarkable ability to maintain contact with the ground, carving a continuous path of destruction for at least 25 miles. Picture a swirling vortex of wind, a dark funnel cloud descending from the heavens, maintaining its grip on the earth for an extraordinary distance. These storms are not mere flashes of fury. They are relentless forces of nature, often spawned by supercell thunderstorms, the giants of the storm world. Supercells possess the unique ability to generate powerful updrafts and downdrafts, creating an environment where tornadoes can thrive. Within this chaotic dance of wind and rain, long-track tornadoes feed off the storm's energy, their rotation fueled by the constant inflow of warm, moist air. As they churn across the landscape, these tornadoes leave behind a trail of devastation, their high wind speeds capable of ripping apart buildings, uprooting trees, and tossing vehicles like toys. However, it's important to note that determining the exact path of a long-track tornado can be a complex task. Breaks in the damaged path, where the tornado may have lifted briefly before touching down again, can make it challenging to confirm the true extent of its journey. Despite these challenges, scientists and meteorologists continue to study long-track tornadoes, piecing together the clues left behind to understand the factors that contribute to their remarkable longevity. History remembers the day as Black Sunday, March 18, 1925. The tri-state tornado rampaging across Missouri, Illinois, and Indiana became one of the deadliest and longest-lasting tornadoes in history. For 3.5 hours, it carved a path of destruction, leaving a trail nearly 219 miles long. Fast forward to May 31, 2013. The Reno Tornado emerged in Oklahoma, becoming the widest tornado ever recorded at 2.6 miles. More recently, in December 2021, Kentucky faced a long-track tornado. This storm left a path of destruction over 165 miles long, reminding us of nature's raw power. Chapter 3. What are the ingredients that transform an ordinary thunderstorm into a long-lasting, destructive force? The answer, as with many of nature's most dramatic events, lies in a delicate balance of atmospheric conditions. First and foremost, long-track tornadoes require a steady supply of fuel. This fuel comes in the form of warm, moist air, which rises rapidly within a thunderstorm, creating powerful updrafts. As this warm air rises, it cools and condenses, releasing even more heat and further fueling the storm's engine. But warm, moist air alone is not enough. To sustain a tornado for an extended period, a phenomenon known as wind shear is crucial. Wind shear refers to the change in wind speed and direction with height. In the case of tornadoes, wind shear creates a spinning effect in the atmosphere, much like a figure skater pulling in their arms to spin faster. This spinning motion, combined with the rising air, can tilt horizontally and create a rotating column of air that stretches from the thunderstorm cloud to the ground. The birth of a tornado. An unstable atmosphere, where air masses of different temperatures collide, further enhances the likelihood of long-track tornadoes. This instability creates an environment where air is constantly rising and sinking, providing the necessary lift and rotation for tornadoes to form and persist. Finally, terrain plays a role in a tornado's longevity. Flat, open landscapes, such as those found in the Great Plains of the United States, offer little resistance to a tornado's path, allowing it to maintain its strength and travel for longer distances. In contrast, hilly or mountainous terrain can disrupt a tornado's circulation, causing it to weaken or dissipate more quickly. Chapter 4. While the United States holds the unfortunate distinction of experiencing the most tornadoes and the most intense long-track tornadoes, these meteorological marvels are not confined to North America. Across the globe, in regions where the ingredients for tornado formation align, long-track tornadoes have left their mark. In the densely populated Indian subcontinent, where the monsoon season brings a volatile mix of heat and humidity, long-track tornadoes have been documented, leaving a trail of destruction in their wake. Bangladesh in particular has a history of devastating tornado outbreaks, often associated with powerful thunderstorms that form over the Bay of Bengal. Across the vast expanse of Canada, long-track tornadoes, while less frequent than in the United States, have been known to occur, particularly in the southern prairie provinces where conditions can mirror those of the American Midwest. South America too has experienced the fury of long-track tornadoes. Argentina, with its Pampas region characterized by flat, open terrain, has seen tornadoes carve paths of destruction for hundreds of miles. Even Europe, often considered less prone to tornadoes than other continents, has recorded instances of long-track tornadoes. In 2016, a powerful tornado tore through parts of Germany and the Czech Republic, leaving a path of destruction over 25 miles long. While long-track tornadoes are a global phenomenon, the United States remains the epicenter of these extreme weather events. The unique geography of the Great Plains, with its flat terrain, clashing air masses and frequent thunderstorms, creates an environment where tornadoes can thrive and in some cases grow to extraordinary lengths. Chapter 5. Today, our understanding of tornadoes has advanced significantly thanks to technological advancements in meteorology. Sophisticated radar systems, including Doppler radar, provide real-time information about a storm's internal structure, allowing meteorologists to detect the telltale signs of rotation that indicate a tornado's presence. Doppler radar in particular has revolutionized tornado detection and warning systems. By emitting pulses of microwave energy and analyzing the echoes reflected back from precipitation particles within a storm, Doppler radar can detect the speed and direction of wind, including the rotating winds within a tornado. Satellite imagery provides a bird's-eye view of storm systems, allowing meteorologists to track their movements, assess their intensity, and issue timely warnings to areas in their path. From space, satellites can observe the development and evolution of thunderstorms, providing valuable data that complements ground-based observations. Despite these advancements, determining the exact path and length of a long-track tornado can still be a subject of debate, particularly for historical events. Ground surveys conducted in the aftermath of a tornado remain crucial for assessing the extent of the damage and reconstructing the storm's path. Trained storm surveyors, often meteorologists or engineers, meticulously document the damage, noting the types of structures affected, the degree of destruction, and the direction of debris. In recent years, storm chasers, equipped with high-definition cameras and a thirst for adventure, have played an increasingly important role in documenting tornadoes and providing valuable footage to researchers. While their daring pursuits provide breathtaking images of nature's fury, they also serve a scientific purpose, capturing data that would otherwise be lost. Despite our best efforts to understand these meteorological marvels, controversies remain, particularly when it comes to historical records. Some researchers argue that certain historical accounts, such as the tri-state tornado, may have actually involved a series of tornadoes spawned by the same storm system, rather than a single, continuous tornado. These debates highlight the challenges of studying tornadoes, even with modern technology, and underscore the need for continued research and collaboration among scientists and meteorologists. As we've journeyed across the globe, witnessing the destructive power and awe-inspiring scale of long-track tornadoes, one thing remains clear. These meteorological marvels continue to captivate our imagination and challenge our understanding. While technology has provided us with unprecedented tools to track and predict these storms, their unpredictable nature and the sheer force they unleash serve as a constant reminder of the power of the natural world. From the infamous tri-state tornado to the behemoth that tore through Oklahoma, these epic twisters leave an indelible mark on the landscape and in our collective memory.